Good afternoon, everybody. Welcome back. If you had joined us for the either or both of the sessions this morning, if not, welcome. Once again, I'm Jim Way. I'm Executive Director of the American Astronautical Society. We've been responsible for putting on these technical session portions of the ISSRD conference for the past few years. We're really happy to collaborate with the ISS National Labs on that. We wish we could have been in Seattle with you this year, but things have changed, as you all well know. And so we're doing the best we can to make sure that we're highlighting the work that's being done in low Earth orbit and here on Earth, and to keep promoting all of the good things that you all are doing. So, welcome again. We'll get started here in a minute, and with the technical sessions, and just want to remind you that this is a 3-day affair. We have more sessions tomorrow and Thursday. You must register for each one of those independently, just the way Zoom works. So please make sure you do so and plan to join us. So, without further ado, let me turn it over to our chair for this session, George Fries, who has been doing this for a long time. He is a founder of Supernal Technical Innovations LLC. George, turn on your mic, turn on your screen, and I turn it on your camera, and I hand it over to you, sir. George, check it in. Can you hear me? Hmm. Okay. Well, we'll see if George comes back to us. Oh,
Uh,
there he is.
okay, apologize for that. I'll also apologize for the camera malfunction. I'll try to get that fixed for tomorrow. But thank you, Jen, for uh, doing this. And we will proceed right away with the first presentation by Dr. Prasad. We'll first present 5-minute executive summary, and then we'll open up for questions for that author. We'll move on to the next presentation author and so forth. After each presentation, we'll have that author come on screen and begin the Q&A from anyone here in the webinar. Webinar attendees will not be able to come on screen, so please use the Q&A tool to submit any questions you might have. If we have time left at the end of the session, we'll address any additional questions that may come along. But be sure to see the full 20-minute presentations. Go online to the program and open up the file as you're interested. Now let's get started with the first presentation.
This is Dmitry Stardubov with the Star Communications. My co-authors for this presentation are Dr. Dubrovin with the University of Arizona and Dr. Prasad with NASA Langley. This presentation is about molten core radiation detectors for missile mission. The motivation for this work is orbital photonics. There is a new space race to replace optical fiber networks with optical communications in space. Uh, the trillion-dollar opportunity here is 60% of the um, global space economy for connecting people and goods using digital communications. The need here is with space hardened materials and solutions that could unleash the full optical bandwidth of space. Next slide shows our background. In 2014, we have reported the first microgravity Z-band fiber on parabolic flight that resulted in multiple exciting developments. Last year, in 2024, we reported the first molten core collide fiber with superior infrared bandwidth. The capability here offers an infrared bandwidth for satellite communications that is um, uh, exceptional even compared to Z-band optical fibers. The challenge is that these fibers have to be tested uh, for optical communications in space environment. And the opportunity here is related to radiation detection market, immediate opportunity. Next slide shows you the design of our planar molten core samples. The samples of collide crystals are sandwiched between two supporting wafers. Next slide shows you our unique capability to detect high energy particles for Luna and Mars missions. Unlike the traditional emulsions, molten core collide detectors have unique reset capability that could be used for sustainable radiation detection. Next slide is the ability of our materials to be used for commercial scintillators, especially for X-ray imaging. Cerium doping of our materials offer high efficiency and fast response for these applications. We are using MISSI mission on the International Space Station for outer space evaluation of our samples. Next picture shows you extensive verifications of our samples. All of our sensor prototypes were accepted for MISSI mission. Next slide is a summary of our science objectives. We optimize the collide crystal composition for high energy particle detection, where we evaluate rare earth doping for scintillator operation in outer space environment. And we also verify the compatibility of molten core process with outer space for possibility of molten core fiber manufacturing in outer space environment. Optimization of cladding materials in our experiment is targeting outer space photonic applications. In summary, our work have targeted new molten core radiation detector prototypes that could be used for Luna and Mars missions. The new photonic materials with broadband optical performance in outer space could be highly beneficial for rapidly growing communications industry. Next slide shows you acknowledgements. Thank you very much.
Okay, sorry about the difficulties there at the beginning. I don't know, had dual monitors going and it caused some problems, but we got it worked out. So George, over to you to monitor to do any Q&A.
Yes, thank you so much, Dr. Prasad, for your excellent presentation. Do we have any questions?
George, can you also allow Dimitri Star to be on the panel so that he could also answer questions?
Jim?
Okay,
Jim,
I'll bring him in.
possible?
Sorry about that.
Yeah.
So Dimitri, if you can hear us, I just promoted you to panelist and jump on in. There he is. Okay. And anybody who's listening, please don't hesitate to ask any questions using the Q&A tool. The panelists are here for you, or the presenters are here for you. George, you have any preloaded questions?
I'd like a little background on how this would be used on the ground. What's the benefit for this?
A great question. The opportunity here is to replace the standard crystalline detectors for X-ray imaging. Compared to the crystals that would take months to grow, our molten core detectors could be fabricated in seconds, and we can make large detectors with a size of up to a square feet for detection. So the opportunity is with X-ray imaging. We have multiple options here. We can detect charged particles with high energy for high energy physics. And with doping, we can change our crystalline detectors into scintillators, so we can do a very efficient X-ray imaging. So the market there is pretty substantial, and it is growing fast. Thank you.
Excellent. So let's see, look like we have some Q&A here. Is there potential to add these sensors to external ISS payloads or satellites?
Once again, great question. I think the opportunity here is with a unique opportunity and capability here is with the missions that go beyond the magnetic shield of Earth. There are charged particles that are not very well studied. The astronauts on translunar Apollo missions, when they closed their eyes, they could see the flashes from those high energy particles. And those effects will be present on the moon and on Mars, because those bodies don't have magnetic shield benefit of Earth. So all the missions that will be going beyond the low Earth orbit will benefit highly from our capability of recording those high energy events. We can record this event in our molten core material, then zap it with laser and reset it to detect particles again. Once again, this is probably the most important capability with our sensor, where we could measure things that others cannot measure. And these detectors are going to International Space Station to record radiation in space environment on the ISS. MISSI mission is the mission of using these detectors for radiation recording on the space station. What is interesting is at the same time, we learned how to make these materials resistant to radiation effects. So when we build these things for radiation detection, we have in mind a huge market opportunity for optical communications in space. Our materials have extended operation range from half to 30 microns. These materials could be used for building photonic chips that would be enabling next generation of optical communications between satellites. Thank you.
Okay, we have another one. Can you comment on applications of this cladding to photonic integrated circuits, PICs? For your information, NASA Ames is investigating use of PICs for future space telescope missions and other applications.
Great question. In fact, we have a unique multi-layer structure, a stack of multiple photonic materials, next generation 3D PLC design with these materials. Photonic chips with claddings and cores enable us to use multiple layers of photonic interconnects with these structures. Indeed, the next generation of photonics will use PLCs, photonic light wave circuits, for most of optical processing. And this design with our claddings, which are specifically designed to be radiation hardened, would be very valuable for photonics in space. Thank you.
Excellent answer. Thank you. One more. If used for X-ray imaging, what would be the disadvantages if used off-planet?
Very interesting question. I think out of the planet, we would have unknown effects of radiation. So disadvantage would be in case if we face some radiation effects that will oversaturate our detectors. And the beauty of our approach is that we can scale up our radiation detectors to fill up the whole dome that covers the space structure. And if we face the radiation effects that are too harsh for our measurements, we always can reset our sensors to their original state. And the fact that we have a stack of these materials allows us to do multiple levels of radiation detectors. So, for example, we can set our claddings to be scintillators and our cores to be equivalent of emulsions that measure high energy particles. So in summary, I don't see too many disadvantages. The flexibility of these technologies mostly gives us advantages over existing technologies. Thank you.
Yes, and the person that asked that question said, great approach. Being able to zero at any time is a great advantage.
Exactly. Thank you.
Don't see any more questions at this point.
Yeah, so we can get going with the next presentation. So Marta, when you're ready, give it a try again. Let's see if it works.
Welcome to the executive summary for KMI's presentation on the reach capture mechanism aboard the ISS. I'm Tom Ziegler, the electrical engineer for Carl Morris Incorporated, and we're here to talk about the reach payload. KMI is a small space logistics company located in Marquette, Michigan. We develop services to protect critical space assets for their operators. Specifically, REACH, our responsive engaging arms for captive care and handling, are an end effector designed for grabbing objects in space, which was prototyped and demonstrated on the ISS, hosted as a payload on the ISSRDC free flyer. The mission objective was to validate REACH by demonstrating the non-destructive capture of a free-floating, unprepared client object. Our REACH demo featured 4 tentacles and was hosted on the ISSRDC free flyer. The tentacles were a scaled-down version of REACH and use artificial gecko adhesive to improve the grip on the client. The client was simulated by a capture cube, which came with replaceable face plates featuring different materials that we could test the tentacles on and swappable by the crew. REACH was equipped with basic capture automation. Over the course of 6 crewed sessions, we had 172 capture cycles or attempts to capture the cube and tested many different combinations of material, orientation, velocity, and such like. We found that REACH was able to capture the cube under a variety of conditions, including a moving and or tumbling target. We had successful captures with each of the materials that were tested. We even effected a capture with one of the 4 tentacles fully disabled, and REACH was able to accommodate for an off-center target. In this presentation, we talk about some of the lessons we learned, including that successful operations require good communication, to always make time for thorough testing before flight, build and troubleshoot with a replica payload, sure you define your interfaces well and test them early, and that remote software updates are, at least in my experience, worth the headache. The next steps for KMI are to build a full-scale 8-arm model of REACH for further refinements of the technology, which will then be hosted on LAYLABS, our flagship small satellite demonstration mission to use REACH to capture and relocate another spacecraft. Following this will be further expansion to improve space mobility, whether that be for active debris removal in low Earth orbit, mission lifetime extension, or an orbital relocation service. We hope you'll join us in the full presentation and the Q&A session to follow.
Thank you for that excellent presentation. Very interesting research. So we have a question here. Great presentation. Could you describe the advantages and disadvantages of using ISSRDC's electrical system to power and command your payload?
Sure. main advantage is we didn't have to do it ourselves. The ISSRDC team had already done a really good job at putting together an excellently designed robot. They'd gone through the headache of getting the batteries approved and the charging dock set up and communications up to snuff with the ISS. So by using them as a platform, we basically had 80% of the headache taken care of for us so we could focus on the actual making the tentacles do what they needed to do.
Very good. We have another question. Does this capture system have both autonomous and manual modes?
Sort of. And funny story related to that. We didn't fully understand how the whole ISSRDC payload commanding setup was going to work when we first started out the mission. So there was at one point the plan to have a controller akin to a Wii nunchuck. For all my KMI employees out there, they love that. But some sort of controller for the astronauts to use directly. We since descoped that. So does it have a manual capture mode? Sort of, not really. The operator on the ground tells Reach that, okay, it's time to start, watching for the cube. And when it is measured within range, it'll start. That was technically software disableable. So there was a manual mode-ish that was never used.
Thank you. So this question, how are you involved with Reach?
I'm the electrical engineer for our engineering team of all of 6 people.
And what was your capture success rate for tumbling relative to not tumbling objects?
That's a great question. I don't have the numbers in front of me directly. I would say if we were hitting 70% of our captures with a non-tumbling target, we hit maybe 40 with. But the metrics are not, I don't think, super representative of the study because we were intentionally trying to force it into edge cases and find the limits of the system.
George,
Okay,
go
so
ahead. Sorry.
Yeah. How large of a scale is a final model of Reach?
As envisioned, it's 8 tentacles, each about 1 meter long. And then on the end of a manipulator to position it relative to the spacecraft. So on the order of, 2+ meters in full wingspan, but with the tentacles can curl up for flight.
Okay. If tasked with running your experiment again, what would you do differently?
That's a really good question, and it's addressed in much more detail in the full presentation because the half of the presentation is really just lessons learned as a ISSRDC payload operator. What would we do differently? I think we just collectively didn't understand the important, the influence of the PIM, and if we were to do it again, would have routed a lot more questions through them instead of trying to figure it out ourselves. Is one of the main things. What would I have done differently personally? A hardware disable on the power outputs to the motors, like a secondary cutoff. I wish I'd done that.
Okay. Do you anticipate the Reach going to be sold to satellite operators, CLDs?
Potentially, yes. The idea is, plan is slap Reach on our demo, mission in space, slap it on a small satellite with a Hall effect thruster, fly around and grab orbital debris. But potentially it could be sold as a standalone product if another company wanted an end effector and had a use in a satellite for it, if that answers the question.
Yes. And I think someone just made a statement here. It's the octopus product.
Yes.
Yeah.
Yeah, a lot of fun with that. The crew, I think, really enjoyed how wacky it looked, and had good fun. The safety panel as well during the review process made many jokes about quote B grade 70s sci-fi horror film.
Yeah, and here's not a question, but their statement is great job, KMI and Reach from the USC team.
Thank you. Thank you. Yeah, shout out to USC for developing the concept initially, and as stated in the full presentation, big thank you to Dave Barnhart and the USC team in general for learning the hard way about the importance of remote software updates if you can do it.
All right, I think we're finished with the questions here. Well, there's one more we'll throw in here. Did you do all this development in-house, or did you outsource a good portion?
We outsourced, we had an implementation partner to help with a lot of the paperwork and stuff. We went through NanoRacks, a Voyager subsidiary. We outsourced some of the machining of some of the aluminum, like pulleys and the tentacles and stuff like that. But otherwise, everything was machined or 3D printed and then assembled. One of the circuit boards I had assembled by an external company, but I did the rest by hand. So almost all in-house.
Excellent. Thank you very much. And we're going to have to get going on the next presentation.
Thank you.
Yes.
Hello, everyone. My name is Trey Smith, and today I'd like to talk to you about the final results of the ISSRDC project. ISSRDC stands for Integrated System for Autonomous and Adaptive Caretaking. ISSRDC was a research project to develop technology for autonomous caretaking of spacecraft, primarily during uncrewed mission phases. Led by NASA Ames with collaboration from NASA JSC, we integrated autonomous intravehicular robots, or IVR, with spacecraft infrastructure, so things like power and life support, and also with ground control. And our focus was on capabilities required for the gateway that also apply to human missions to Mars and beyond. Our approach was to test with existing IVR on the ISS, like ISSRDC and Robonaut, as an analog for future IVR on Gateway. However, due to delays in Gateway program phasing of IVR development, ISSRDC pivoted partway through, changing its near-term infusion effort to target operational use of IVR on ISS, that is, with ISSRDC. This talk will mostly focus on results during the last year of ISSRDC, which was FY24. At the end, we'll also have a brief retrospective about some earlier contributions of the project. Our FY24 focus areas were targeted inspection and survey. Now, since this is the 5-minute executive summary video, I'll just leave you with a teaser video and one wrap-up slide. If you want to see more, come to the talk. This video will give you a sense of what it looks like when two ISSRDCs are performing multi-robot mapping together. The overall survey consists of multiple panoramas, one panorama per bay of the module, and each panorama consists of 56 SciCam images taken with the camera pointed in different directions. So the ISSRDCs spend most of their time looking in different directions at the same location, and then occasionally you'll see them move from station to station. However, the ISSRDC project was active for 4 years. During that time, it's been a very broad study of intravehicular robot integration. And just looking at the FY24 capstone demonstrations we talked about today won't give you a full picture of the topics we've studied over the years. Some examples of topics we looked at in earlier years included logistics management with heterogeneous robots between Robonaut and ISSRDC, and we also looked at integrated 3D user interfaces. Over the years, ISSRDC has accomplished many firsts, including the first time a robot navigated between modules of a space station, the first time a robot located a sound source in space. This was a collaboration with the Bosch USA Sound C payload team, and also the first time a robot mapped the interior of a space station with the results intended for human visualization. And the project had lasting contributions, including our research publications and developing future NASA talent through intern mentorship, and also open source software that we've contributed both to the ISSRDC robot software and our own ISAAC software repository. You see links there. Now, infusion of this technology to future missions. We're very interested in the Gateway Intravehicular Robotics Subsystem. It was our original infusion target, but it's still on hold until development of the IVR subsystem itself progresses further. We're looking at production use on the ISS. We successfully matured an ops approach for performing interior surveys of the ISS using ISSRDC. ISS operators are very interested in it. They like using the resulting panoramic data sets and believe that the automating the surveys could save crew time. Unfortunately, given the realities of the ISS budget situation, the program is currently not able to invest in sustaining these periodic ISSRDC surveys. And then, we're also interested in other opportunities, including the Commercial LEO Development Program and the Earth Independent Operations domain of the Mars Campaign Office.
That was an excellent presentation. Congratulations on such a successful product. I've had a lot of sessions with ISSRDC, but we have one question coming up here. How difficult would it be to combine the capabilities we see here with robotic and effectors and enable autonomous removal of payloads from visiting vehicles and their storage inside the space station? The stevedore function. And could the unit change out plug and play components?
First off, can you guys hear me? Great. Yeah, so I think those are great types of tasks for next generation intravehicular robots, whether they be free flyers or use other mobility modes. We identified, working with the Gateway Intravehicular Robotics Working Group, that two of the major use cases would be cargo transport or general logistics management. So things like when an uncrewed visiting vehicle arrives at Gateway, and Gateway is also uncrewed, if you can transfer the cargo into the modules and even have the visiting vehicle leave and go into disposal prior to arrival of crew, that could save the crew a lot of time. Another example is basically a very wide range of utilization tasks. So for a lot of these stations, maybe the bulk of the sustaining operating costs are going to be launching crew and crew consumables. So if you can sustain useful operations during uncrewed phases, you can reduce your launch tempo a lot, and it can be a huge cost savings. ISSRDC itself is not really designed to handle these use cases. The arm is not very dexterous. The propulsion is not very forceful. It would be very helpful to have multiple arms, or think of like an arm or two and a foot in order to be able to apply forces to things in a way that ISSRDC can't right now. But future robots certainly ought to be able to handle some of those cases.
Thank you. So we have another question. Great presentation. How much vision does ISAAC have? What kind of resolution?
Well, I'll take that to be a question about the ISSRDC robot platform. Of course, the ISAAC project didn't develop ISSRDC, but we are sort of one of the flagship guest science users of ISSRDC over its history since it was launched in 2019. So we have many different cameras on ISSRDC with different functions. Let's see, looking forward, we have the SciCam, which is, gosh, I want to say it's a 20 megapixel imager. It's kind of like a cell phone camera class camera. Can record RGB video and can stream live video to the ground. And we also have the HazCam, which is a depth imager. So it returns point clouds. Can be a little bit tricky to register those two cameras output to each other because it's not a single RGBD imager. But I guess I'd be happy to talk more about the different uses of them if there are follow-up questions.
Okay, Jim, you have a question?
Yeah, Trey, can you just talk a little bit about what you foresee as the impacts of AI on everything that you're doing here? Do you see that as being, something that can really enable the development of this and push it a lot further than you could without?
I would say yes. There's a lot of interest right now in the broader robotics community in, what you might call embodied AI. So things like using foundation models you can almost imbue a robot with common sense about how to manipulate common items. Something like the ISS, there are hundreds or thousands of different dexterous manipulation tasks that astronauts are called upon to do. You can't have a PhD researcher spend 6 weeks to program a robot to do each one of those tasks. So if you can use techniques like this to address a really wide and broad range of them together, I think there's a lot of potential there. It's also very difficult because the safety story is incredibly important. The software assurance story is incredibly important, and so I think we're kind of working our way forward incrementally on those kinds of issues.
So we have any other questions? Not looking like any around.
One more, George.
Okay.
It's in the Q&A tool.
Yes. Can Isaac be teleoperated from Earth or from orbit to a planet's surface?
Well, Astrobee in general, we have an approach of basically nominally autonomous operations. So an ideal Astrobee activity, you push one button at the beginning of it, it does the whole thing by itself and cleans up and heads back to the dock, and then it's done and you never had to do anything. But we also try to design for continuous operator oversight when possible. So the ISS does have loss of signal periods when communications are lost, and Astrobee will continue operating through those periods. But we try to have an operator in place when possible because there are anomalies that arise, and our fault response is, definitely doesn't have 100% coverage. Trying to think of, and Isaac really goes hand in hand with that approach, and if anything, kind of elevates the level of abstraction that you can command Astrobee at, because one of the things that we performed in the final ISS campaign was automated planning, so that you could extend that push button approach to an entire survey of a module, and the higher level Isaac executive would send lower level commands to the Astrobee API to complete that.
Okay, we have one more. Could those software developments be made using a graphical user interface? That would help with not needing a PhD scientist to do all of the software mods.
That's a really interesting concept. I'm a big fan of easy to use graphical interfaces during operations because workload for mission operators is a big problem, and anything you can do to make that easier is great. I'm a little bit less keen on graphical interfaces for software development because somehow it always seems like a great idea, and then once you get to using it, it turns into a mess. That's been my experience, but maybe the latest round of tools is better at that.
Okay, do you see any other questions, Jim?
I just see just one more.
Okay,
And yeah,
here we go.
yeah, and then we'll move on.
Okay. Are there any cross-border data regulatory difficulties, tech development, or implementation ISAC faces in working with the partner space agencies?
Well, again, I'll take this to be about the ISSRDC facility as opposed to the ISAC project, since we're just a guest on the platform. I think that it is sometimes complicated to work with international partners. We've been very lucky that we've been able to get approval to open source release ISSRDC's flight software, and we can often release some of the big data sets into the public domain. There's even been an effort where we collaborated with some Korean researchers to release a robotic localization data set that you can find online that basically they massaged the data set to be in the same format that is used by a lot of different robotic localization researchers. So basically you can try out any localization algorithm you want on ISSRDC data in this zero gravity environment. So it's a very unique type of data set. So that has been really helpful, but I don't think it solves all of the problems. And we often have to wait a little while to go through data release processes and try and stick to that.
Okay, thank you so much for your research and attending today.
Thanks, everyone.
So we have one more, Jim, or?
We actually had two more, so.
Okay.
Go ahead with the next one, Marta.
So here I will be giving a quick recap of the initial results from a quantum space technology demonstration called SEEK. My name is Kelsey Ortiz. I come from the University of Illinois Urbana-Champaign. I'm a fifth-year physics PhD student working under Paul Kwiat in his quantum information group. So there are certain applications where we might require a quantum network. Some of them are scaling quantum computers, providing secure communication channels via quantum key distribution, having further non-locality research and distributing entanglement at longer distances, and quantum sensing applications like quantum telescopy. So future quantum networks will be made up of space quantum links and fiber optic quantum links. And the reason why we would want to do a space quantum link is because fiber losses actually limit the distances of fiber links that you can have to less than 100 kilometers before losses become too high. So space-based platforms can have less loss as the photons are traveling simply through air. However, with space-based platforms, there are definitely new challenges to overcome. So there has been other activity in quantum space, mostly led by the Chinese, but there also has been activity of payloads sent to space from Singapore, Italy, and Germany. However, there hasn't been a US-led experiment yet, and that's where the Space Entanglement and Annealing Quantum Experiment, or SEEK, comes into play, as it is the first American quantum communications experiment in space. And essentially, it's a 6U payload. It's externally mounted on the International Space Station right now, and it creates polarization entangled photons, as well as it has a detector annealing system. And this payload is self-contained, so it's not distributing the photons to Earth. So the first main goal of SEEK is to create and verify entanglement space, and the way we are doing this is via two tests. One is called the Bella inequality violation, and the other one is taking quantum state tomography measurements in order to actually measure the entangled state of our photons. In our system, we have a never-before-flown integrated waveguide source, and we are also demonstrating a single liquid crystal tomography system whereas normally other systems require 2 liquid crystals or 2 wave plate components in order to do a tomography. The second goal is to combat radiation damage on the avalanche photodiode detectors that we have as our single photon detectors. And the way we are doing this is through laser annealing, so essentially having a high power laser and heating up the detector in order to reduce start counts. With this, we're hoping to show that you can increase the lifetime of these quantum payloads that have these specific detectors on them and learn about the repeatability of laser annealing. So here's a quick look into the optical system. It is a 405 pump laser that goes into a SPDC waveguide source. And then we also have an 810 nanometer annealing laser that goes into the system and is directed to the 4 detectors for annealing. Here is a quick look inside the payload, and you can see various free space optics and fiber routing, as well as lots of epoxy. So SEEK launched on November 4th, 2024 via Aegis Aerospace from the Kennedy Space Center in Florida. It is now mounted on the materials on the International Space Station Experiment platform and can be seen on that picture there on the right, circled in red. So our CHSH Bell violations have been successful. Our first violation we got is a 2.58 that shows our system is demonstrating non-locality, and our highest thus far has been a 2.65, and we have shown a higher quantum state fidelity than Mischius and a statistically stronger violation than the spooky payload. Since then, we've been able to take a lot more Bell violations, as well as monitor our detector dark counts as the radiation increased the dark counts, and perform some detector annealing via 2 methods of thermal annealing and laser annealing. So the current timeline is that SEEK will be returning for post-flight analysis May of 2026, but there is a potential for an additional 6-month extension, which would bring it to November of 2026. This would allow us for more time monitoring radiation exposure on the detectors and doing some more annealing tests. So this project would not have been possible without our various collaborators and the various graduate students that worked on this payload. So thank you very much, and looking forward to the questions. Hello, everybody. Good to be here.
Thank you so much. This is very exciting research. And let's see, we have a question. How did you choose the wavelength of the power and the power of the annealing laser?
Yeah, so the wavelength of the annealing laser is an 810 nanometer diode laser, and essentially we chose that wavelength to match the optics for the down converted photons. So in our system, we have a 405 pump laser that then goes into a spontaneous parametric down conversion source that makes our photon pairs that then we're creating entanglement from. And so all the optics were for 810 nanometers. And so for this system, we chose the annealing laser to match that wavelength so it could fit into the system nicely. And then for the power of the annealing laser, we distributed around 1 watt of power per detector. So the overall laser has a 4 watt output power, but around 1 watt of power is what other literature and other research has performed annealing on these detectors. And specifically, a collaborator of ours at the University of Waterloo, Thomas Yenevine, has done ground-based measurements on these detectors and at ground-based annealing, and has shown that 1 watt seems to be the most optimal power to do that annealing before any damages start occurring. So higher than 1 watt, it seems like permanent damage starts to happen on these semiconductor detectors.
Okay, thank you. Which temperature did you use for the thermal reset of the detectors?
So yeah, for the thermal annealing of the detectors, we went up to, our target was going up to 100 degrees Celsius, but we actually only were able to reach between 70 to 80 degrees Celsius. This is because it actually depended on our payload temperature, how high we were able to push that TC on the detector. And so it did vary between 70 to 80 degrees Celsius. And we performed that thermal annealing test for about an hour versus when we do laser annealing, it only requires a minute of exposure time from the laser.
Okay, thank you. Could you explain, not like to a fifth grader, but to this the audience here, what's this thing called the anonymous Bell violation?
So the Bell inequality violation, yeah, I go into it a little bit in more detail on the 20-minute talk, but essentially it's this S value that is calculated from looking at different coincidences between our photons when we're measuring it in different bases. And essentially what this value does is it lets you calculate whether you have stronger correlations than you would with classical systems. So essentially what you need to know is that with this S value, if it's less than 2, then you have a classical system. And then if it's a greater than 2, then you violated that inequality and your system is showing non-locality. So it's a good metric that a lot of people in the quantum field use just because it's good to show, okay, is your system showing greater than 2? And how high can you go with that? Theoretically, with like a perfect system, you would only be able to achieve a value of 2.82. And for SEEK, we're measuring Bell violations around 2.6. This varies quite a bit with our payload, and I talk about it a little bit more in the 20-minute presentation, but this is dependent on the payload temperature again. So I think in the future, we would definitely be doing more temperature stabilization of our system.
Okay, so are you engaging with companies, and if so, what are their roles?
Yeah, so this collaboration for this project included a company called ADVR Corporation. So they were the ones that actually produced the waveguide spontaneous parametric down conversion source. And we've continued to do collaborations with them in our research group. And yeah, I think we're continuing to work with them on developing their sources, improving their sources, and then testing them out in different environments like in space.
Okay, I have another question. So why, what is the advantage of doing this on the space station versus the same investigation on Earth?
Yeah, that's a good question. So essentially, we wanted to use this as a technology demonstration to show you can build a robust enough optical system and entanglement source to survive the launch vibrations, to survive the different temperature fluctuations. These kind of entanglement sources are easy to build in a lab setting where you have nice optical tables, temperature is controlled. You don't have to worry about alignment of your optical systems and trying to keep coupling into fibers. And so we aimed primarily to do a technology demonstration and kind of learn about the operations of these entanglement sources in space. And then the second, I would say, is looking at the radiation that's impacting the detectors, which was one of our main goals.
Excellent, thank you. So one more, any plans to talk to Earth terminals?
So I don't quite understand that question. What do you mean by talking to Earth terminals? Like distributing the photons to Earth, or?
Well, right now you said that it was self-contained, so I think, yeah, he said yes.
Yeah, sure. So with this experiment, it would not be possible. I mean, we don't have any optics that would be able to distribute it onto Earth, but there is work right now that we are doing in our research group, looking at future projects and the potential for doing demonstrations of things like satellite to satellite, demonstrations from satellite to Earth. But right now, they're just initial studies looking at kind of what kind of count rates we would need, what kind of losses we would have via through the atmosphere. So I would say just early stages thinking about doing an experiment like that.
Okay, so Jim, you see any other questions? No? Okay.
No, I think we're good.
Thank you so much for your research and joining us too.
Cool. Yeah. Thank you for the questions.
Thank you, Kelsey.
Great talk. Yeah, that's a comment from the.
Thank you.
Yeah.
All right, George, I think we have one more presentation. I don't think the presenter is here, but it's supposed to be Adarsh Rajguru. I don't see you in the attendee list. If you are in there as under some other name, please let us know. But we are going to go ahead and try to run the presentation. But I'm not sure if there's going to be any Q&A since the presenter isn't here. So Marta, go ahead and run that one. Thank you.
Hi, welcome to my presentation. Today I'm going to talk about the demonstration of clingers, which is an experiment that we carried out inside the ISS. First, let me give you some background. This research is about rendezvous proximity and operations and finding a new way of doing RPO that can save fuel and time. Currently, RPO is done between two entities where one is designated as a servicer and the other is designated as a client. The client does not participate in the RPO, and the burden is on the servicer. Hypothesis posed for this research is that the performance of this approach can be significantly enhanced if both spacecraft engage in active communication and perform coordinated maneuvers during all phases of RPO. This research proposes a new RPO strategy from phase 1A onwards to enhance the safety, resilience, autonomy, and efficiency of RPO. The central idea is to move beyond the traditional servicer-client paradigm and instead investigate the benefits of two actively maneuvering spacecraft coordinating their approach. We have created simulations of the new RPO approach and validating the models with experimentation. The Holy Grail test is performing all experimental verification of all the phases of RPO in 6 degrees of freedom under true microgravity conditions. For that, we have built the Clingers experiment for demonstration inside the ISS. Clingers stands for Compliant, Low Profile, Independent, Non-Protruding, genderless electronic RPO sensors. It has a suite of sensors for target acquisition and resolution and a docking mechanism to enable docking. Clingers has an IR camera and a collection of IR LEDs as part of its sensor suite. The IR camera detects the LEDs and uses a perspective and point algorithm to determine precise relative position and orientation from the target. It uses Bluetooth to communicate with other clingers to exchange position and orientation information in order to reduce errors during relative navigation, thus streamlining the proximity operations. The journey of Klinger's experiment started from a 1D ground testbed, building the merit of using the PNP algorithm to identify and resolve the target. Then it progressed to a 3 degree of freedom test on a 2D air-bearing platform. Once the RPO algorithm was developed using this testbed, engineering development units of Klingers were built, and these units were tested at the AstroB ground simulator in NASA Ames. This testbed was also a 3 degrees of freedom 2D testbed on an air-bearing platform. The difference was Klingers were able to mount directly on AstroB simulators on the ground, and we were able to test and troubleshoot the handshake between Klingers and AstroB, mimicking the interface of the flight units with the AstroBs on board the ISS. After all the flight acceptance testing of the Klingers were done, we launched Klingers to the ISS and conducted several science missions. We performed 3 different modes of RPO inside the ISS. Mode 1 was when both servicer and client were actively maneuvering and communicating between each other to cooperatively perform RPO. This is the mode where we were able to show maximum saving on delta V and time. Mode 2A was when the client cannot maneuver but can reorient for the servicer to get within the field of view for the servicer to resolve the target. It can also communicate in this mode with the servicer to perform some degree of cooperation during the RPO. Mode 2B was when the client cannot maneuver nor reorient but can communicate with the servicer during RPO. And mode 3 is when the client was not able to play any active role in RPO and all the burden was on the servicer, which is the current way of doing RPO missions. So far, we have conducted several science missions of clingers on board the ISS. In each science mission, we have attempted several runs and attempted all the modes of RPO. During each run, we have collected data and used it to correlate the results to our ground simulation models.
Okay. And once again, I don't believe we have that author with us. We normally wouldn't show the presentation if the person wasn't here, but again, in the with the objective of sharing research with everybody and making sure it gets out there, we decided just to show that. So I don't know if we can take or entertain any questions on this one. George, do you have any other comments on this?
Not on this one, no.
Yeah, okay.
Oh.
All right. So Lynn Harper is just saying this is enabling technology not just for LEO, but for planetary and asteroid missions. And she has a question, but sorry, Lynn, we can't answer. So what I will offer is that all of these presenters should have their contact information in their presentations that are available online. All of these executive summaries that you've seen are available there, as well as their full 20-minute presentations. So please go on and check those out and take a look at those, and then contact the presenter if you do have any follow-up questions. George, did you have anything else to offer before we close it out?
No, thank you.
Okay. All right. Well, I think that does it for the day for today's sessions. Tomorrow we will kick it off again tomorrow at noon. We have workforce development and STEM education, followed after a short break by in-space production and applications, and then wrapping it up tomorrow with commercial and non-governmental use. And then Thursday, we do it all again starting at 9 a.m. with biotechnology and medicine, then human health and performance, and then fundamental biology. So Yashvi, please just go to the online program. I put it in the chat, but I will send it to you as well. But the online program has everything in it. All right. That does it for today. Thanks again very much all for attending, and we'll see you tomorrow. Thanks.